Hi guys, Tim's back again. Nice to see you, except I can't see you, of course. What to say? I hope you're doing okay and you're not too bored, you're not getting too stir crazy. I could do with the football starting back up again. Even behind closed doors would be good, but never mind. Anyway, I'm going to carry on teaching you the NMR stuff. Now, NMR's tricky and difficult. Takes me a few videos to go through. So you need to be in the right frame of mind to look at these and want a bit of intellectual stimulation. For that's what I'm going to try and give you, okay? And work your way slowly but surely through. There are some packs, but I don't want to give you the packs till I've done a certain number of videos, and then you can look at that. So if you're in the right mood and you fancy learning how to do this and getting your head around it, fine, but pick your way through it carefully, pick your way through it slowly, and you should be okay. All right, guys, chin up, and I'll crack on and we'll see where we go, okay? I'll see you, so yeah, lovely. All right, off we go then, yeah. Okay, now if you look at the last NMR I did, I'm looking at low resolution NMR spectroscopy, because that covers three things. I think from the top of my head, it covers your peaks, where your groups are, where your environments are, how many protons are in each environment, the integration. It basically covers, if you like, 90%. The splitting, which I'm going to come on to, is an embellishment, an enhancement of low resolution into high resolution, and gives you important information that you need to be able to interpret. So before I get on to that, let's just have a quick run through in this video of a few more low resolution spectra. Okay, so this will be, I suppose, this is, I think, the fourth video in the sequence on NMR. So, low res spectra. Okay, guys, low res spectra. A few examples. Okay, I'm going to use a lot of esters for this, because esters are quite popular. We'll looking at other things. We'll deal maybe with some difficult ones, different ones later. But I'll stick with esters for now. So all I'm going to do with you is just talk through what these spectra will look for various low resolution, i.e., no splitting, a number of different possibilities that hopefully you'll grasp where I'm coming from. Okay, so number one, let's have a look at this. An ester, classic ester, CH3C double bond O, single bond O, CH2 CH3. Okay, now if I can fit a few on by squashing things up a bit, it's going to help you. I think this is actually relative intensity. Alright, this is chemical shift. And I don't need to go all the way up to 12, because if you look at the chemical shifts of the groups in this particular ester molecule, I go up to about 4. That'll encompass them all. It allows me to spread things out a bit and spread the scale, make it clearer for you. So 4, 0, 2, 1, 3. Okay, right, now although I'm going the other way, you have to interpret these. There's one thing that links everything together, and when you do these, if you do these questions in an exam, you need to put a table together to interpret the spectrum. I'm going around the opposite direction, but doing a table is vital, because if you can't interpret the structure, you get marks for at least interpreting the spectrum if you can't deduce the structure, which is worth having. Okay, so this table, you've got to be strict with yourself and make sure that you do it. And anyway, it helps you. So the table takes different forms depending on what you're doing, but generally you've got an environment column. This should be done on the exam paper, normally from the spectrum to the table, but here I'm going from the structure to the table, to the spectrum. So environment, chemical shift, integration, and there will be a fourth column splitting in the next video. So we'll just stick to 3 for now. Right, environment, let's have a look. How many environments have I got? How many different environments? I've got environment 1, there's 3 protons in that environment. I've got environment 2, there's 2 protons in that environment. I've got environment 3, there's 3 protons in that environment. No problem at all. So then, bearing that in mind, so going from left to right, here we are. So if I go from these 3 here, chemical shift values and all of that, we're talking C, so we're talking H joined to a C, which is joined to another C, double bond O. No doubt, if you look at your chemical shift table, that there is H, I just said it between 2 to 3. Chemical shift 2 to 3. Integration, there's 3 in that environment. H, C, C, 3. Looking at these 2 here, so that's number 1. Now look at number 2. These are going to be split because they're adjacent. Another video for that. Okay, those 2 there, single bond O. If you look at your chemical shift table, H is joined to a carbon, joined to a single bond O. That occurs in the region of about 3 to 4. When you're actually doing these, make sure you're very accurate where the peaks are. I'm being a little bit general with these numbers, but they're fine. 2 in that environment. Number 3. Okay. These very common, a bit misleading, but basically a hydrocarbon chain indicated by that and here. And these are often split 0.5 to 2. And there's 3 in that environment. So again, low resolution. So we just simply plot those out. Peak there for 3, 2 to 3. Peak there for 3, 3 to 4. Peak there for 2. Low res, okay. Integration, relative intensity might be overlaid on the top, telling you how many are in each environment. So basically, this one here. So not in the same sequence as I've drawn them in the molecule. The peaks don't appear in the same place. So you've got to think about this. Yeah. So over here are these 2, 3 to 4. Those 2. H is joined to a C, joined to an O. That's the chemical shift for them. These here, H is joined to a C, joined to a C, double bond O. There, 3 of them. Right, and finally, these 3 in a hydrocarbon chain, out of the action, out of any major sort of things like that. Right at the bottom end, 0.5 to 2, as always with those 3 in that environment. There's your spectrum. Okay, for that. Anything else to say? No. Number 2. Right. Next one. Same idea. C, H, 3, C, H, 2. Again, very similar to the one above. An ester linkage, CH3. What I'm saying is you stop the video, you draw these, hope I'm not in the way, you draw these, have a go at drawing, do that now. So stop the thing, pause it, right, and then see whether your table and your spectrum matches mine. Okay, so don't just wait for me to do it if you're serious about this. Okay, environment, chemical shift, integration. Okay, so what have we got? Actually, with the one at the top, just make it clear this one. 2 to 3. I'm just identifying them. That's number 1. Number 2, 3 to 4. So that's number 2. That's number 3. Okay. Right. This one underneath, same deal really. I don't know which way you want to go. Seem to have gone this way. 1, 2, 3 different proton environments, end of. So let's start on this one. It's always like, that's hard because you want to go, I don't know, right to left or left to right, but the actual where the peaks appear jumbles that up. So you're always having to think, constantly check, where am I at, which am I looking at, which part of the molecule am I looking at. There's a lot of things you're thinking about all the time. So we'll start with that one. Chemical shift 3 to 4. Those are these. Integration, there's 3 of them. No problem. Then we'll go to 2. 2 in that environment. You look at the one above, that H is joined to a C, which is joined to a C double bond O. H is joined to a C, which is joined to a C double bond O. Okay. 2 to 3 is the environment for those. These are classic NMR environments, okay, and there's 2 protons in that environment. Finally, those there, it's very similar to the one above. Very similar. HCr. That'll be 0.5 to 2. And there's 3 in that environment. There. Quite similar to the one above, but not exactly the same. Right. Draw the spectrum of that. Okay. Relative intensity. Again, don't need to use a full scale. Fit it all on, just going from there to there. 1 there. 3 there. Okay, so let's draw this. 3. So going backwards, 0.5 to 2 chemical shift, there's 3 in that environment. Okay. I'm going along 2 to 3, there's 2 in that environment. And 3 to 4, there's 3 in that environment. Okay, so there you go. Now let's get the integration on. Try and sort it. So those there are those 3. Proton 3 down the bottom end, no problem. Integration of 3. Those are those 3. The next are 2 in that environment. There they are. Integration of 2. So those are 2. Number 2. 2 in that environment. And finally there'll be 3 in that environment. And now H joined to a C, single bond O. 3 to 4. Integration of 3. So those are number 1. So these numbers, make sure you know what's what. Integration values, how many in each environment, those are just numbers to tell the examiner that I know what's what. So I should be doing this. 3, 2, 1. So there you go. Subtly different, but similar. For you. Okay? Good. Right. Let's be clever.